Okay, so after we introduce the differentiability and analyticity, and we're going to examine that a convergent power series will define an analytic function, and actually an infinitely differentiable function. So 2.5 proposition, let f of z be sigma n from 0 to infinity a sub n z minus a to nth power have radius of convergence r greater than 0. Okay, then a for each k greater than or equal to 1, the series sigma n from k to infinity. Here's n from 0 to infinity. Here's n from k to infinity. So n minus 1, n minus k plus 1, and times a sub n z minus a to the power n minus k. This new series has radius of convergence, r, the same r. They are going to basically first part A, just claim this each k. For k equal to 1, you have a series k equal to 2, you have another series k equal to 3, 4, 5. So you have a sequence of series. They all share the same radius convergence as the original series. Part B, f, this function f is infinitely differentiable on this open disk centered at A with radius r, and the case derivative is given by, oh, this one has a number. This is 2.6, has given by the formula 2.6. Okay, so this actually not just a random series. It is the case derivative. And part C, for n greater than or equal to 0, then we can say that actually the coefficient a sub n is not random. It's tightly related. It is 1 over n factorial, the nth derivative of f evaluated at A. Okay, so it's totally it's uniquely determined by the evaluation of nth derivative. All right. Okay, now we are going to prove this this proposition. After this proposition, we can see that actually we have a large class of analytic functions, all convergent power series will be analytic because it is infinitely differentiable. Analytic just continuously differentiable, not even twice differentiable, based on by the definition. But here is infinitely differentiable. Okay, so now let's try to prove it. So again, we assume that A is equal to 0. This center, we just assume it is 0. We just shift it. It's not the big deal. To simplify. And second, how do we get this sequence of series? The sequence of series based on K. Actually, we only show part A for k equal to 1. K equal to 1, what do we do? We start from f, we get the case k equal to 1. So let's see. So we have f and k equal to 1, we get n from 0 to infinity. Here it becomes n from 1 to infinity. N a n z minus a to n minus 1. Here you see n minus kk is 1. We show this, check this. After we check this part, we consider this as the original sequence. We consider this as the original sequence, then k equal to 2 is actually just the same step. The same step, n minus 1 minus 1. N minus 1 minus 1. The same, exactly the same step. So this one is a repeat of the previous step. Because we already verified or checked the first step, this one is done. And then you can continue this for whatever steps. Many times of steps is always done. So it's enough or it's sufficient to show the case when k is equal to 1. Okay? Okay, now let's see. Remember that at the beginning of the last video, we recalled this is definition of a radius of convergence. And now we need to show that we need to show that 1 over r is equal to the lim sub of, this is n times a sub n, take power 1 over n. Why we take power of 1 over n? Because an is a coefficient of a z minus a to nth power. This n does not come from here. It comes from this n. But now a sub n, it is coefficient of a z minus a to power n minus 1. So you're supposed to put 1 over n minus 1. Right? 1 over n minus 1. Okay, so we need to prove this. We need to prove this. And by the L'Hopital's rule, we have the limit n approaches infinity, ln of n over n minus 1 is equal to 0. Well, that's a easy conclusion. So this conclusion implies the limit n approaches infinity, n to the power 1 over n minus 1 is equal to 1. Okay, so this part does not contribute anything. So it suffices to show that the lim sub of ops value of a sub n to power 1 over n minus 1 is equal to 1 over r. Okay? Okay, so we are going to prove this. We're going to prove this. Well, let's see. I don't know. I mean, it is a lim sub. It exists. So set 1 over r prime be the lim sub of ops value of a sub n to power 1 over n minus 1. We set it to be 1 over r prime. We show r prime is equal to r. Okay, then r prime is the radius of convergence of the series, power series of what? N from 1 to infinity, a n z to power n minus 1. Remember, we assume a is equal to 0, so there's no a, just z to power n minus 1. And you shift the coefficient a little bit, and from 0 to infinity, a sub n plus 1, z to n. You shift it from 1 to 0, it becomes a plus 1. A sub n plus 1. A sub n plus 1. A sub n plus 1, what this is? This is what this is? This is a1 plus 2, no, a1 plus a2z plus a3z squared, and so on. Right? So this one is. And then what we can say, this part, if we multiply it by this sequence by z, we will get a1z, a2z squared, a3z cubed, and so on. So this is exactly a series n from 0 to infinity, a n z n, but without a0, All right? So if z has ops value less than r prime, if it's inside the disk of convergence, then this part converges. It converges. Then it implies this part converges. Right? So it converges, then hold on a second. Yeah. Then what we get? Converges inside it, it's uniformly converges. It's actually like this. So sigma n from 0 to infinity, a n z to n ops value, uniform convergence. It's less than or equal to ops value of a0 plus ops value of z sigma n from 0 to infinity, a sub n plus 1 z n, right? It is finite. It is finite. So it's uniformly convergent. So every point when its ops value is less than r prime, you get here convergent. So r prime should be less than or equal to r. Should be less than or equal to r. Okay? And the other one. If ops value of z is less than r, then this series converges absolutely. And from 0 to infinity. Absolutely, right? It converges absolutely. Well, if it's 0, then nothing we need to discuss. 0 is always a finite sequence. You only have a0. If it's not 0, 4 point, if it's not 0, then we check here. A sub n zn. This one, it is going to be less than or equal to 1 over ops value of z times sigma a n z n and plus a0 over z. This is absolute convergent. This is fixed number. We're talking about each single point. It's finite. It's finite. So this implies r is less than or equal to r prime. R prime less than or equal to r less than or equal to r prime, so they equal to each other. So that sequence of a series together with the original series have the same radius of convergence. Have the same. All right. Okay, so we finished the proof of part A. The part A is checked. Now let's see the part B. We're trying to show the differentiability. We're trying to show differentiability. So let Z in the convergent disk. We're going to show, actually, this one is, where it is? Yeah, what we are going to show, this one is actually the derivative. We're going to show this is a derivative. So we prove that this one is a limit. Okay, so let's give it a name. So let g of x be sigma n from 1 to infinity n a n z directly z to n minus 1. No a. N a n z to n minus 1. Okay, and f is sigma a n z n. So we get partial sum k from 0 to n a k z k and k from n plus 1 to infinity a k z k. Partial sum plus a tail, and this part is called s sub n of z. The remainder is Rn of z. This is Rn, this is Sn. Okay, so we break them. Okay, so now let W be in ball centered at 0 with radius R fixed. Fix it. Okay, and choose R with W less than R less than capital R. Okay, so we choose, whenever we have a point, opposite value and R, between them there's a third point. We want to use a slightly smaller disk to cover this W. Okay. So we are going to show that the f prime of W exists and is equal to g of W. Okay, so exists means differentiable. Is equal to g of W means it's given by the previous formula. Okay, and now what we're going to see. This is 0. It's a large disk R. And then W possibly is here. Then there's a smaller disk with radius little r. And we're going to focus on the close neighborhood of W. Okay, so this is what the letter is, delta. Okay, so choose delta greater than 0 such that the closed ball centered at W with radius delta, and take closure, it's completely contained in the ball centered at 0 with radius R. So it's inside the small disk. And so far we just randomly pick up small enough delta, and later maybe we will even restrict it. Okay, and in this small disk, let Z be in this small disk. Then we compute. Exists is equal. We just directly show the difference is small. That's enough. So that's what we do here. See, so we are going to compute the ratio Z fz minus fw over z minus w, and take the difference with g of w, and then we will push z close to w. When z close to w, this ratio will give us f prime of w, minus g of w. We wish the difference becomes smaller and smaller, eventually becomes 0. Okay, so f, remember f, we have the partial sum and the remainder. So f of z, we have partial sum and remainder. F of w, we also have partial sum and remainder. So we have 4 terms. We have 4 terms, okay? So let's see how we organize those 4 terms. So I will have Sn of z minus Sn of w, z minus w. And Rn of z minus Rn of w, z minus w. This is together will give us f of z minus f of w over z minus w. And here we insert Sn prime of w, the derivative of the partial sum, plus Sn prime of w, and minus g of w. Okay, so why? You see here, this one, partial sum, is a polynomial. If you let z approach w, this is exactly the derivative. The polynomial is differentiable, so its limit is exactly the derivative. So this limit will approach 0. This will disappear. Will eventually approach 0. We're going to show all 3 parts will always approach 0. Okay, this approaches 0 for sure, always. And here, rest of the part. Let's see why they approach 0. Okay. Let's look at this remainder. Rn of z minus Rn of w. Remainder, here's the remainder. In the remainder part, you will have akzk, akwk. You factor out ak, you will have zk minus wk. I remember this one we can factor it. It's ak z minus w and z2k minus 1 plus z2k minus 2 times w and da da da. And then you have wk minus 1, right? Remember that we have such stuff. Okay, so let's see. So it is a sigma k from n plus 1 to infinity ak z2k minus w2k over z minus w. And after we factor it, you see here, this is z minus k from numerator. Here you have denominator. They cancelled. They cancelled. You only have what? You only have sigma k from n plus 1 to infinity ak, then you have z2k minus 1, z2k minus 2w, and w2k minus 1, w2k minus 1, right? And then in the book they gave us a very smart estimation. This part, how many terms? There's k terms. It's k plus 1. There's k terms. By the triangle inequality, it's ups value of z to power k minus 1, ups value of z to power k minus 2, ups value of w, and ups value of z, ups value of w, k to w to power k minus 2, and plus ups value of w to power k minus 1. Well, you see here, z is possibly here. Let's put the z here. What is little r? This is little r. From 0 to r, this is little r. W is here, z is here. So ups value of z, ups value of w. They're both less than r, so each part will have r. How many copies? So k copies of r2k minus 1. This is k times r2k k minus 1 from this graph. Okay, so by the triangle inequality, we can estimate each term AK, this one, upside value of AK, upside value of K, RK minus 1. Right? Correct? And we know that this is even this R is inside the absolute convergent series. We know this series K from 1 to infinity, K from 1 to infinity, K upside value of AK R2K minus 1 converges. You already put the upside value and you choose this point inside the convergent disk. It converges. So for epsilon greater than 0, there is an integer, capital N1, such that for all n greater than or equal to N1, the tail, this tail from n plus 1 to infinity, this tail is dominated by, well, epsilon over 3. Epsilon over 3. Right? This directly comes from the convergence. Okay? It's from the convergence. And Sn prime of W converges to G of W. Why? Sn prime, if you examine it, it's actually the partial sum, because Sn prime of W is the partial sum of G of W. G of W is a power series, and this is partial sum. So there is an integer N2 such that for all n greater than or equal to N2, upside value of Sn prime of W minus G of W is less than epsilon over 3. Less than epsilon. And then we choose n to be N1 plus N2. Well, in the book, they say they choose a maximum. It doesn't matter. I just choose large enough so that those both conditions are satisfied. So I prefer to choose N1 plus N2. They are definitely maximum. Okay, choose n equal to N1 plus N2. Then these two inequalities are preserved. Are reserved. Okay, so once we fix this n, then we are back to SNZ minus SNW over Z minus W, and then minus Sn prime of W. Well, this one will tell us the delta. It is less than epsilon over 3 if Z is sufficiently close to delta. Okay? Here you need to go back to the delta part. The first delta guarantees that this small disk is inside, this small disk centered at the W is inside this middle disk. And this delta is guaranteed the polynomial derivative inequality is satisfied. Okay, so combine 1, 2, and 3. Combine those 3 inequalities, we have that f of z minus f of w over z minus w minus g of w is less than epsilon if z minus w is less than delta. In this part, you do not see capital N, but in order to find the delta, you need first to get the capital N, and then you back to the delta. So you get the first derivative, then you have the second derivative, third derivative, and so on. So we always just prove the first one, and the rest of the part is just repeating of the first case. And part C, an is 1 over n factorial's nth derivative evaluated at a. Well, you see, first of all, the nth derivative how do I write? I don't want to make, okay, n equal to k, not k equal to n. Kth derivative. That's why I feel confused. n minus 1, n minus k plus 1, z minus a to power n minus k. So this is the derivative. When we have the derivative, let's check the first derivative. F prime of z is a1, a2, z minus a, and a3, z minus a squared, and so on. And then if you evaluate f prime of a, the rest of the part are just 0, so you have a1, so a1 in this. And 1 factorial is 1, so there's nothing wrong. F double prime of z is 2a2 plus 6a3 z minus 2, z minus a, and plus that's 4 times 3 is 12, a4 z minus a squared, and so on. And then when you evaluate f double prime of a, it is just the first one, 2a2. This implies a2 is 1 over 2 f double prime of a, the same thing. And f kth derivative evaluated at a based on this formula, you will see that only first term survives. Okay, so when n is equal to k, the first one, n is equal to k, so you will have k minus 1, n is k, so k minus k 0 plus 1 is 1, so times 1, and that's it, and times I'm sorry, I miss a n is k, and times a k, and this is a factorial, k factorial, so it's a k factorial a k. So ak is 1 over k factorial f k's derivative evaluated. So all the tails after you evaluate at the center disappear. All the tails disappear, vanish. You only have the leading term, non-zero, constant terms. So that's part C. Okay, so the proof is very long. It took us like 30 minutes, but it's not that difficult. Well, the important proof is the second part, part B. How do you get the order? The order of capital N and the delta is very important in this proof. You cannot reverse the order. So try to read the proof. If you have any question or doubts, send an email to me. Let me know. Okay? So this proof is very useful and interesting. The the strategy is very interesting. Okay. Okay. The first part is simple part. Okay, so we finish this lecture and we will continue the discussion in the next lecture. Thank you very much.